welcome to the stage. Great person that also advocates for software, Bassem Dghaidi from GitHub.
Thank you, Tambi.
Thank you.
All right, amazing. This is a very lovely crowd. Marhaba. We have a lot to talk about today, and the easiest thing for me to do is to actually come here and tell you what to think and how to think and what is my perspective about the future of software engineering, right? But what I actually want to do in this talk is to help you derive these conclusions yourself from me presenting some information for you and from me presenting some premises for an argument I'm going to be making throughout this presentation. But first, let's do some housekeeping stuff. My name is Bassem Dghaidi. I'm a senior software engineer. I currently work at GitHub. It's actually today my 4th year anniversary. And I work on GitHub Actions specifically, and hopefully GitHub Actions is a product you all use and hopefully love. And I promise you we're trying to make it better as well. We're working on the next iteration of GitHub Actions, which is going to be really, really awesome for you all. I create technical content in my free time by working 7 days a week. It's not really ideal, but it allows me to do two things that I enjoy the most, working as a software engineer, but also sharing my passion for this field with everyone who wants to listen. And I was born and raised in a rural Lebanese town, and I speak Arabic very well. بحكي عربي كتير منيح. A lot of people ask me this. And I immigrated to the Netherlands for about 5 years now. And my Dutch partner, who is a psychologist, no, she does not psychoanalyze me, at least as far as I know, or as far as she has told me. So with this brief about me, let's dive into our topic today. We're going to do a small journey through the past. Then we're going to talk a little bit about the present. And then we're going to venture a little bit further into the future. Okay? So entertain me here as we go through the history of software engineering from the 1800s. And I promise you, it's not going to take too long. So first of all, let's start with a quick question. Do we discover the future? Do we create the future? Or do we recreate the past? This question might be evident for some of you. It might not be very evident for others. And for the philosophers amongst you, you're going to ponder this for many hours to come. So keep this in the back of your minds as I go through my presentation right now. We're going to start our journey in the 1800s, and specifically in 1896. A lot of you have known a little bit maybe the story of Ada Lovelace. She was Lady Ada. She was a mathematician. She's coming from an aristocratic family. She met Charles Babbage, who created the first mechanical computer. And Lady Ada was actually one of the first programmers of that mechanical computer. But we're not going to talk about her today. We're going to talk about Annie Cannon and her group of female computers. What many of you don't know and realize, that the term computer was actually used to denote and to describe human beings doing computations. And Annie Cannon and her group were part of a group at Harvard called the Harvard Computers Group, which worked on cataloging the stars that we see at night. They worked with pickings on building the first catalog of stars using their spectral images and their intensity. These are the stars that we see today, and this is a catalog that we still use today. Unfortunately, and quite misogynistically, Pickings thought that this type of work was sort of beneath him, so he sort of delegated this to the group of amazing computers. But what Annie did at the beginning of her career, she was able to catalog 1,000 stars within the span of 3 years. By the end of her career, she was able to catalog 3 stars within a minute. And by the end of her entire journey, she was able to catalog 200,000 stars. And this is where the journey of computation actually began, with human capabilities, with human abilities to do this sort of computational work. Moving on a little bit to 1936, making a jump to Germany, actually, with Konrad Zuse. And Konrad created the first computer, actually, and the first programming language called Plain Calcul. And in a different world, had the Second World War did not happen, maybe Germany would have been the leading in terms of computation instead of sort of the US and parts of the West nowadays. Jumping to 1944 with John von Neumann. A lot of you know, von Neumann architecture. It's at the basis of all of the CPUs that we use today. This architecture was created by John von Neumann, who is a polymath by every definition of the term. I mean, being a polymath like von Neumann is definitely an ambition for many of us. But he's fantastic. He's a fantastic mind, and his contributions to the field were amazing. 1948, Ruth Teitelbaum, she worked on the ENIAC computer. You can see her crouching right over there. These gigantic machines were programmed by literally plugging different switches. And the reason why we're going through this history a little bit is I want to show you how the practice of software engineering evolved and how we sort of moved through time and how we started dealing with different levels of abstraction. We have Maurice Wilkes, who introduced the concept of subroutines. He introduced the concept of macros. We have Grace Hopper, who in 1952 introduced the idea that machine or programming languages could be independent from the machines that they actually run on. You might not think that this is a groundbreaking idea, but back then, programming a certain computer required you to directly interface with it. Grace Hopper introduced the idea that we could build programming languages that operate at a higher level of abstraction, which can be generalized to different machines, different architectures. And from that came COBOL. We have Margaret Hamilton, who actually coined the term software engineering. And I'm cherry picking from this timeline, but I highly encourage you to read more about this timeline later on. I'm going to share with you my deck so that you can go through this history, which is a beautiful history. So in 1963, she worked on the NASA Apollo missions. She actually wrote the software for some of these devices that went onto the rockets and onto the moon, actually. The term software engineering did not exist before that. Fred Brooks, who doesn't know the book, The Mythical Man Month? Everyone jumping into management, you are told you should read The Mythical Man Month. This is the person who actually wrote this, and he introduced a lot of different concepts to our vocabulary and to what we talk about and how we talk about software engineering today. Edgar Dijkstra. I live in the Netherlands. Edgar lived and did his research in the Netherlands as well. Not only did he create the A-star algorithm for discovering the shortest path, his seminal work in actually structured programming, he created the concepts that we know today: sequences, iterations, the reserved keywords, the idea of blocks of programming, how you can write your statements within blocks, if, then, else, all of these conditionals, iterations. These are the brainchild of Edgar Dijkstra, and these concepts came in 1969. So again, we moved from plugging plugs, punch cards, then we move on to programming languages that are machine independent, and now we have structures in our programming languages. Barbara Liskov, and again, I love how the history of computation sometimes does not mention these female legends, literally, who contributed a lot to our field. Barbara Liskov introduced abstract data types. Everyone who has taken a computer science course has studied abstract data types. You learned about queues, stacks, priority queues, all of this stuff. These are the brainchild of Barbara and her work. And actually, if you have used the solid principle with object-oriented programming, you're told to learn about the solid principles. One of the principles is called the Liskov substitution principle. Guess who Liskov is in this case, right? Now, moving on a little bit to 1978 with Leslie Lamport, who developed LaTeX. So if you've done any advanced research, graduate level research, you have obviously used LaTeX. But more importantly, Leslie introduced a lot of the concepts and theory behind distributed systems. Now everybody comes in and talks about microservices and distributed systems and how we can scale and build for whatever. But in 1978, the theory was discussed back then for these concepts that we are heavily utilizing today. So you see the lag between conceptualizing these things and when we get to actually use them in practice. Brad Cox, in 1986, developed Objective-C, which influenced how much we think about, or how we think about modularizing our code and how you can use programming languages to create more modularized component or component-based engineering. You know, React today is quite popular, but these ideas that React reintroduced into our vocabulary and how we work are not new at all. They're as old as 1986. And obviously, there's a lot more amazing people that we can go through. Eric Gamma, if you've read anything about design patterns, Eric Gamma is one of the co-authors of the book. If you haven't read the book, I highly encourage you to do so. It's related to object-oriented programming, obviously. And everybody who's transitioning to a more of a senior role, you're told you should read design patterns and understand a little bit how they work. Some of these things are practical. Some of these are not as practical as they were before. But again, it introduced the concept of patterns to our vocabulary and to how we do software engineering. Mary Shaw, 1995, she advocated for recognizing software architecture. So again, she brought a new term for how we talk about software engineering in general. She brought the idea that architecting a system is different than engineering a system, and it's different than actually building a system. Jeff Dean, who is a legend. Everybody who's doing machine learning knows Jeff Dean. Anybody who's doing distributed systems knows Jeff Dean. Anybody who worked or knows anything about Google knows that Jeff Dean is one of the pillars that allowed Google to be what it is today. If you don't know him, I highly recommend that you read some of his papers. It's amazing, phenomenal work in terms of scalable systems, big data, big query, big tables, but also machine learning, and a lot of the models and systems that we see today are, exist because of Jeff Dean. Eric Evans, Bobby Wolf, Linus Torvalds, and I think we're using an old presentation, by the way, for some reason. But anyway, I updated this in the morning. Linus Torvalds, he created Git, distributed version control. Obviously, he created Linux, but what I want to introduce here is how much he influenced the paradigm, or he introduced the paradigm shift when it comes to software engineering by introducing distributed source code management. Before that, a lot of different systems existed, ClearCase, CVS, and so many others, but Git was distributed. It allowed you to do local software development, but at the same time, it allowed you to do to work and engage with others, and that's why GitHub exists today as well, because Git facilitated this sort of distributed work. Moving on to 2008, we have Andrew Schaefer and Patrick Dubois, and I promise this is the last slide about history. It's not going to be more of a history lesson. They introduced the concept, or they coined the term DevOps, which also changed how we think about how we work and operate and how we manage our software and systems. Now, why did we do this history lesson? If I plot all of these contributions through time, you can see on the x-axis we have the years, on the y-axis we have the years, and on the x-axis we have all of the different contributions. You will see an interesting pattern. You will see a linear trend line, not an exponential one. But everybody's been telling us that technology evolves at an exponential rate. Everything is so fast. The time difference or time delta between when changes are introduced is so small and it's getting incrementally smaller. That is true for the technology parts. Not so much about the practice of software engineering. So our practice has evolved very gradually through time and through the years until we got to today's world. So keep this in mind. This is going to be the first premise of the argument I'm going to be making, and there are two more premises that I would like you to learn about before we make our conclusions. What is modern software engineering? Right? So we talked about the history. Let's talk about the present. This is a system. This black circle is a system. We're not going to draw a black box because we understand how the system works. And on the left-hand side, you will see a few boxes connected to it with dotted lines. And these boxes, they will denote the forces that are applied on these systems. So what I'm going to be doing now with you, we're going to be building a mental model about software engineering as a practice. And we're going to be using this mental model to understand a lot of what we perceive or how we perceive software engineering in different companies, different parts of the world, different industry verticals, and whatnot. So compatibility. Who hasn't dealt with the compatibility of systems and modules and how these different systems integrate together? Complexity. We obviously deal with complexity some of the time. Other times we don't. It's a varying force that sometimes exists at higher levels and sometimes exists at lower levels. Context. Who hasn't asked about what is this system for? What do we use it for? Why are we building it? The 3 questions that I always like to ask and that I talk about in my real-life system design videos is, why are we building this? Who are we building it for? What are we building? The how of building it is software engineering, right? Which is what we are supposed to answer as software engineers. This is all part of the context. Then we talk about cost, schedule, resources. These, you need to think of them as forces that act on our ability and limit, sometimes constraint, and sometimes they permit us designing our systems in a certain way, and they facilitate going in a certain direction as opposed to the other. Obviously, cost is a big concern for a lot of different companies. And a lot of hyper-growth startups, cost sometimes is not a concern. A lot of engineers are told that money is thrown at them, go build, we want to get to market, we want to dominate globally. Cost is not a problem. Schedule sometimes is an issue for some. It might not be an issue for others. Resources as well. And I like to think of these forces as interconnected. And that's something you need to keep in your mind as we go through this exercise, that these forces are codependent. They are dependent on each other, which means that when you change the value of one, it has to impact the value of the others. It's inevitable. You cannot have everything all at once, and if you have nothing, you're not going to be able to build systems, right? So they are codependent on each other. The relationship between them is something that is very difficult to come up with. So the function or the formula of how all of these things play together is very difficult to come up with, but they are dependent on each other. Then we have development, deployment, and the evolution of systems. How are we developing our systems? What do we use to develop our systems? Technology stacks, the choice of programming languages, is part of that development force. If we choose one stack over the other to solve a certain problem, we might get a suboptimal outcome. But if we choose another, we might get better results. How do we evolve our systems? Did we build them with the appropriate patterns that will allow us to scale them to reach our objectives? Did we build them in a way that allow us to integrate at a much easier rate or not? And how do we deploy them? I'm still surprised that some people deploy, once every 6 months, and then they tell me that, we have a lot of regulation, we have a lot of, constraints on us. We cannot really deploy many times a day or even many times a week. And this is where the legal element as a force comes into play. In a lot of sectors, there's no option. You are regularized, you are governed by a lot of external entities that force you to do certain things in a certain way. But also more importantly, and this is something that a lot of software engineers forget quite often, which is the ethical element of our practice. We forget that we have a choice in the technology we build. We forget that the technology we build has an impact on human beings every single day. And this is something I want you to keep in mind as we go through this deck. The ethical component is very important, specifically today in the age of AI and large language models. Security, safety, reliability, performance, and functionality, all of these are also forces that, affect how we design our systems. Now, these numbers are fictional numbers, obviously, but they represent the weights of each of these forces and how much they affect how we design our systems. And these numbers, this is just given here as an example, right? I see people taking pictures. This is not science. This is just an example. These numbers vary depending on the company you are in. They vary depending on the industry you are in. They vary depending on the geographical region you operate in. They vary on the purpose of your business and the reason why you're building software in the first place. So in a lot of companies, you will see that legal applies a much heavier force on how we design our systems, as opposed to other companies where legal takes a step back, but for example, development, deployment, and evolution have a higher weight. And the practice of software engineering in these companies varies drastically. The experience we get, the subjective experience and the developer experience we have is totally different. And this explains why you will experience software engineering so differently than, for example, folks in big tech, or folks in smaller companies and startups, or folks in hyper-growth companies, right? So keep this in mind, first of all, when you design systems, but also when you choose where you want to work and which companies you want to help build and get to the future. So this exemplifies modern software engineering, and everything that has been said so far is not, the brainchild of my own genius. It's actually the work of a very fantastic man called Grady Bush. Some of you might know Grady, some of you might not, but Grady is, if you have actually used UML, Grady is the creator of UML. He's also in the list of folks who introduced a lot of awesome things to software engineering. So if you've used flowcharts and sequence diagrams and all of that stuff, Grady brought these into our practice. Grady is also a historian. He's an IBM research fellow, and he created this amazing timeline, which I used a little bit here, and created a rendition of it. Now, how much of software engineering can LLMs do? So we talked about two things, two premises were made right now. We talked about the history. We talked about all of the forces that apply to software engineering. Now we're going to talk about AI. How much of software engineering can LLMs do? And this is a fantastic visualization. It's actually coming from a video for one of my favorite YouTube channels. It's called 3 Blue, 1 Brown. And if you don't know it, I highly recommend that you go and check out the work of Gary. It's amazing. He's a fantastic mathematician, but he does these amazingly beautiful visualizations, and he explains a lot of complicated mathematical concepts in very, very simple terminology, and in a way you can really understand it. And he has a course, free course online, discussing large language models, how they are built, and discusses the math behind large language models. So I highly recommend that you go check out this video to understand how these models work. And before we discuss what LLMs can do, we need to talk about their problems. And as working at GitHub, as a company who builds on top of these large language models, some folks might not be happy with this slide, but I want to share with you the ground truth so that you are able to make your objective conclusions and understand effectively how to use these tools. We can never use any technology effectively until we understand how we use it, or how it is actually, we cannot use the technology effectively until we understand how it is built and how it functions. So number one, autoregressive large language models, which are basically everything you see today in ChatGPT. Who has used ChatGPT so far? Can you raise your hand? Okay, it's a good group. Has anyone used Copilot, GitHub Copilot? Fantastic, probably around the same group. And has anyone never ever used large language models at all? So everybody in this room has. Perfect. You've obviously noticed that they are non-factual sometimes, and sometimes they are toxic, even though these things can be filtered out. But the idea is that these cannot be made factual. Impossible, by design, period. Okay? They are not controllable. You can apply filters on top of them, but you cannot change intrinsically their behavior and how they come up with the probability distribution. The way they are built is with a big data set. And the data set heavily influences the output that you're going to get from these large language models. But in addition to that, how they are trained and the model's architecture also influences what comes out on the other end. But these models, a hill I'm willing to die on, these models do not reason. They can calculate a probability distribution, but they cannot think for themselves, no matter what anybody tries to convince you otherwise. The probability that the produced tokens can diverge us outside of the set of correct answers is extremely high. In fact, this is the probability formula, and it's a divergent formula. It's a divergent function. They can never converge. So if you look on the right-hand side of the tree of possible token sequences, this is the red. And again, possible for any given prompt. The green tranche is actually the tree of correct answers. So the probability of a large language models landing on a sequence in that tree is very, very, very low. Relatively, of course. That's why there's RAG, there's fine-tuning, so sometimes you can just push these models in a certain direction, but you can never force them to always give you the correct answers. They use a fixed amount of computation per token, and this is right now what the war or the arms race that is currently happening. These models cannot, in the current architecture, of course, we're not talking about different architectures, they cannot be optimized to operate at a lower cost or to produce tokens with a lesser cost. That's why everybody's fighting the hardware war right now. How do we benefit from the economies of scale of hardware so that we make it cheaper for everybody to use these large language models and provide us with the ability to embed them everywhere we want? This is what's going to fulfill the promise of large language models, but right now it's still a problem that is currently being figured out. So, going back to the question, how much of software engineering can LLMs do? A fraction of the development work. That's what they can do. They can help you brainstorm some of the other functions and forces. They can help you brainstorm the legal, they can help you brainstorm the security, but they can never give you any confidence in any of these other elements. What they can do is they can suggest things for you, and the place where they can suggest things that are useful falls within the development part. So out of all of these different functions that we as software engineers work tirelessly to balance, we are people who don't only, write code. As much as many people want us to think that this is the only thing we do, we don't. We are the people who balance all of these forces, and we make sure that our systems get to a state of equilibrium in spite of all of these forces acting on it. That's our job as software engineers. That's fundamentally what we do. We make sure our systems get to a stable state all the time. And whenever one of these functions or forces changes, applies more weight or less weight, it's our job to come back and stabilize these systems. Autoregressive LLMs are still very useful. They've proven to obviously be great programming companions. If you've used GitHub Copilot, you know that it's actually quite helpful. I personally use it every day. I've used it since it first came out, and I'm always impressed by what it's able to do for me. They can remix different forms of art. They can help you with your mental blocks. And finally, they're very helpful to non-native speakers. This is something that's often disregarded. But a lot of folks don't speak English as their first language. And English is actually a very heavy barrier for them to progress in programming, in software engineering, and in their career as well. Large language models will help you attenuate some of these issues for you and for others. Gergely Oraz, who is a, how do you say it? He's a technical writer. He often has a lot of spicy takes, but sometimes he also has a lot of interesting deep dives into technology, and I highly recommend that you check out his newsletter. He says, got to give it to the GitHub team. This is us or me patting ourselves on the back, but bear with me a little bit, because he says, while most AI developer tools are aiming for a workflow that takes a spec and much later generate code, with no developer input, GitHub created a developer-driven, AI-assisted workflow. Let that sink in a little bit. So some companies are coming in and saying, oh, software engineering is dead. Bye-bye, no more job for everybody. And that couldn't be further from the truth. This is the strategy that GitHub has adopted because we know the limitations of these large language models. We know what they can do. We're not going to overhype them. We're going to give you tools that are actually beneficial for you today, given their limitations. And what I love about this specifically is Kyle Daggle is the COO of GitHub. He says the secret to AI isn't creativity, it's reducing toil. And toil is basically all of these activities that we have to do as software engineers when we write code that are not necessarily fun. They're not really the problem-solving parts. They're just writing boilerplate code or some of the boring aspects, or maybe filling in a JSON struct so that we can, decode some input coming in from another system and stuff like that, right? The interesting parts of software engineering are left to you as software engineers. So don't be afraid of using stuff and tools like Copilot. Actually, they are here to take away the boring parts of your work so that you can focus on the more interesting things. And again, this is Thomas Domke, who's the CEO of GitHub, who's talking about, GitHub Copilot and large language models actually breaking down the language barriers and whatnot. So, with that said, we talked about three things. We talked about the history, we talked about how our practice evolved over time, we talked about the present, we talked about what constitutes modern software engineering, and third, we talked about large language models, and I hopefully helped demystify them and help you understand them a little bit more so that you can know how to use them. So now the last question remains is, and this is the answer for our argument, how do we prepare for the future? And preparing for this future is not about surviving this future. It's about thriving in the upcoming phase as software engineers, right? That's what I care about. That's what we should all be caring about. So obviously, I'm going to pick a time horizon, which is 5 to 10 years, because that's what the information we have today can allow us to, extrapolate a little bit further. Anything beyond that point in time, it's science fiction. So anybody who's talking about 10-year, 20-year, 30-year time horizon, they are talking science fiction. This is hype. They have their own agenda. I'm not going to speak to that. In 2017, Andrej Karpathy wrote about software 2.0. This is 2017. And if you don't know Andrej Karpathy, he's one of the legends in the field right now. I highly recommend you also follow him on Twitter because he's a great, great engineer and he's a great thinker. And he's one of the best educators in this field. Again, if it hasn't been a mistake in the slide deck, there would have been a link for one of his YouTube videos where he literally creates a GPT live in a couple of hours. And he breaks down all of the ways you can do that yourself and follow along, which is a great, great video. He says, software 2.0 most often the source code comprises of the data set that defines desirable behavior, and 2, the neural net architecture that gives the rough skeleton of the code, but with many details, being the weights to be filled in. This is his perspective of the future of software engineering. This is what he thinks about how we're going to be writing code in the future. And if you notice, this is yet another higher level of abstraction. So we started with the code, bare metal, plugging things. We moved on to programming languages that are machine agnostic. We added structure to these programming languages. We created different types and variations and flavors of programming languages, right? We added a lot of things to our vocabulary. And now is the time to think about models as ways with which we can solve future problems. They don't necessarily need to be super high intelligent things. They can be domain-specific models that solve very specific problems that just we can mix and match to derive solutions for complicated issues. So in the 5 to 10 year horizon, change will not be all of a sudden. We're not going to wake up one day and have AGI dominate the world. That's just not going to happen, okay? The change will be gradual, and it will be expected. We're going to see it coming. And if you follow the right people who build in public, you're going to be able to sort of predict and expect what's coming up next. That's just like what I do. Number 2, LLMs are not it. I don't care what Sam Altman wants to promise or what he wants to say. LLMs, no matter how much you scale them, are not going to spin up AGI, period. Okay? LLMs are just yet one more evolution in this space, and they have proven to be useful in specific use cases. They have their limitations, and they're not going to be able to scale indefinitely. They have to abide by the laws of scaling. Objective-driven architectures are going to emerge, and this is not necessarily what we're talking about today, about agent-driven development. Agents are not going to be the solution for the large language model problems. Objective-driven architecture are. This is Jan LeCun. I highly recommend that you also look up Jan. He's a fantastic researcher, and he is currently the most outspoken person, about trying to ground the hype and the expectations about AI and whatnot. And you will understand a lot about the future of these models and whatnot from him. Number 3, human-level AI is beyond this time horizon, beyond the 5 to 10 years, but we will steadily continue to make progress towards it. There's a lot of problems that need to be solved in this space, and we will continue making progress towards that point. And finally, AI-assisted development will only get better and better with time. And last point I want to make, stop fighting and competing with the machine. Okay? It's time that we stop having this conversation about which is better, humans or machines or whatever. it's inevitable that computers are going to be better than us in a lot of different things. Period. That's a ground truth. Okay? So now what we need to do is we need to think of ways with which we can control this machine to help us evolve and solve our future problems. That's what we need to focus our energy on. SAS is dead. Long live SAS. SAS is dead in the sense that it's a technically solved problem. You've seen Suhail yesterday talk about 2,000 or 3,000 microservices, and they are able to scale indefinitely and solve a lot of different engineering issues. In my opinion, the SAS era is gone. Now we have a new era that we need to focus on, and it's going to usher, the future of our field and our progression. Ramp up on the fundamentals and build depth in the hard sciences. I cannot state this enough. Again, in my other slide deck, I had links for a great book called The Mathematics of Machine Learning. It's still being under development. Great author, which goes through all of the math you need to understand how machine language models work and how you can build your own. Even if you don't have an engineering degree, you can go through and follow along with that book because it starts from the primitives. Less focus on syntactic sugar and more focus on what's happening under the hood. Stop worrying about syntax, for the love of God. We are software engineers, programming languages are tools. Let's just use them for what they are. Let's use our tools to solve problems and less worrying and about geeking out. And geeking out is fun, don't get me wrong. I can argue with you all day long that Go is the best language in the world, but but that's not the point of why we do software engineering. That part is the fun part. And the spotlight shining on solving human problems will only get brighter. Because at the end of the day, it's not about tech. It never was. It has always been and will be about solving human problems. Okay? Programming will go back to being a hobby for many of us. A lot of us have forgotten what it feels like to enjoy programming and just build for the fun of it. We are doing this professionally for many, many years, and sometimes that takes away from the enjoyment of writing code and solving problems. So what I predict in the next 5 to 10 years is that these areas are going to witness a lot of contributions coming from AI-assisted models and what we call AI today. Nobody can see past the singularity, so when the singularity happens, which is going to be the point when we create artificial general intelligence, if we get to that point, nobody can predict what's coming up next. That's the realm of science fiction. There are plenty of books, and I can recommend many for you to go and explore that realm of humanity's evolution. But the last thought I want to leave you with is, and going back to the first questions I asked, in many ways, we're going to be discovering the future. But right now, we have a responsibility to try and create a better one together. And this can only be done, with all of us involved. Thank you so much, everyone.